All right, now you can also have a flux through a closed surface, and that's what we're going to be most interested in terms of electrostatics. So by a closed surface, I mean, like, suppose I have a cube. Well, that cube has 6 surfaces to it, 6 flat surfaces, and I can envision talking about the electric flux that goes into and out of that cube. So I could have an electric field that penetrates through the cube, and I can define a total flux for the entire cube dependent upon the flux that goes through each one of those 6 surfaces. Or I could have a sphere in space, a 3-dimensional sphere, and if I have an electric field through that, I can define a flux going through that sphere, and you can see at some parts of the sphere the flux is going into the sphere, and in some parts of the sphere the flux is going out of the sphere. Okay, and what we're going to find out in a minute is that the total flux depends upon the amount of electric charge that's actually located inside of the surface. So let's take a very simple example of this. Let's take this cube and turn it on its side. So we're looking at it from the side, and it's got a flat faces that has a top and a bottom and another side, and then put an electric field that goes through like this. So this is E. So the electric field is going through this face and that face, and it's going parallel to the 2 side faces and to the top face and the bottom face. All right. Let's define. We have to define a positive direction. So let's, for each of these surfaces, define an area vector. Okay. That. And the total flux that's going through this box is just going to be the sum of all the fluxes going through each of the sides. So the total flux going in the box is equal to the sum of 4 sides. This side, that side, this side, that side, this side, and the back side. All right? Now let's see what's happening on these. Let's look at the 4 sides, the top, the bottom, and the 2 other sides that are towards you. In each of those cases, the electric field is moving in the same plane as the A vector. For instance, let's look at this side that's pointing is closest to you. There's an area vector that's actually coming out of the blackboard there. And so the electric field is going this way, the A vector is going that way. They're perpendicular to each other, so the cosine of 90 degrees is going to be 0, and there's going to be no flux, no electric flux coming out of that square side. In the same way over here, on the top surface, the electric field is going that way. This area vector is going up. There's a 90-degree angle. The cosine of 90 degrees is equal to 0, so there's no flux going through that surface. So if you look at it in this case, then there's no flux going through 4 sides, and the only 2 sides of this cube which have any electric flux going through them are going to be this side and that side. All right, so everything is equal to 0 except for the flux out of end 1 plus the flux out of end 2. All right, this is 1 and this is 2. All right. Well, the flux out of end 1 is just going to be equal to the electric field times the area. Well, let's see, the electric field is going that way, the area is going that way, So that's going to be cosine of 180 degrees, which is minus 1. So this is going to be equal to minus E times A. The flux out of N2 is going to be equal to E times A times the cosine of 0 degrees. So that's just equal to E times A. The electric field on this end is parallel to the area. And so if we add these together, we're going to add minus EA and plus EA. And the total flux we're going to get after doing all these calculations is that the total is just equal to 0. Okay. Now if you just look at it, this kind of makes common sense. Imagine that this electric field line showed the flow of water. And you've just got a pipe that's carrying water. Well, you've got as much water goes in as comes out. And so there's no accumulation of water in there. There's no change in water in the box. And so the total flow, the total flux in the box is going to be equal to 0. As much comes out as goes in. All right? That's all there is to flux, is to figure out, is the flux on an object, a closed object, is you just sum up the flux over the different parts of the object, and then you do the calculations for each part. Notice that we've brought it in this case so that the electric field is constant over each part, and that the angles are constant over each part. All right, let's do another. Suppose I took that same square box, cubical box that I was looking at a minute ago, and rotated it by 45 degrees, like this. So I've still got a front face and a back face, but now I've just rotated it by 45 degrees, and I'm in the same electric field. So there's E. I have my 4 vectors for each of the surfaces. There's I'll call that A1, A2, A3, and A4. Okay. The electric field is going to go parallel to the surface on the top surface and the bottom surface, so there's not going to be any flux through 2 of the surfaces, and the total flux through this box is just going to be the sum of the flux through 1 plus 2 plus 3 plus 4. Phi 1 plus phi 2 plus phi 3 plus phi 4. All right, well, once again, the flux through any part is just the electric field times the area of surface times the cosine of the angle between the electric field and the surface. So for instance, phi 1 is just going to be equal to E times A times the cosine. Let's see, in this case, E is going that way, A is going that way. It's going to be the cosine of minus 45 degrees. Okay. Let's look at phi 4. Phi 4 is going to be equal to E times A times the cosine of, let's see, E is going that way, A is going that way, so the angle we're concerned with is right here. That's a cosine of minus 135 degrees. Now if you think about it a minute, that cosine has a negative, is the negative of that number, because in this case we've got the same amount of flux going out as going in, so phi 1 is actually going to be equal to phi 4, and if you go ahead and you calculate these two parts, A2 and A3, this flux is going to be equal and opposite to that flux, and once again when we do this calculation we're going to find that the total flux is equal to 0. Okay? Alright, so that's 2 very simple examples of how flux is calculated. One thing you want to remember is that if you have the electric field going in the plane, of a surface, the flux has to be equal to 0. If the electric field is pointed opposite the direction of the surface vector, you may get a negative flux. You can have positive flux and negative flux. In general, when we have a closed surface, we're going to be talking about the net flux coming out of the surface. Okay.